In this first lesson on kinematics, we're going to look and see how we can use a displacement time graph to sketch both a velocity and an acceleration graph. Right, the first things we need to identify are the vector quantities we're going to be working with. The first is displacement. Displacement is the vector version of distance. Now, a vector quantity means that it has both direction and magnitude. So the difference between distance and displacement is that a displacement has a magnitude. So if we start off with x as some function of time, so displacement as a function of time, we can then derive two other quantities. The first is velocity, which is rate of change of displacement over time, or dx dt, otherwise called x dot or f dash t, or sometimes x dash 2, I suppose. Acceleration then is rate of change of velocity. So the one I haven't written on here is acceleration is actually dv dt, so rate of change of velocity, which is also the second derivative of displacement, written as x double dash or f double dash. A couple of things to think about is it almost always helps to draw a diagram when dealing with kinematics problems. It just helps you get an idea of what's actually going on in the situation. Also really important is to identify what the difference between instantaneous acceleration and velocity is, and average acceleration and velocity. So for instantaneous acceleration and velocity, this is the one we find by finding the derivative. So those values written above are instantaneous acceleration and velocity, whereas the average acceleration and velocity would be v2 minus v1 over t2 minus t1, just looking at the way in which the velocity has changed over time. So very important that you understand the clear differences between average and instantaneous acceleration and velocity. In most of this topic we'll actually be working with instantaneous. Okay, so a typical type thing we might be asked to do is we're given a graph of displacement of a particle and we want to start thinking about what a velocity graph might look like. So remembering that velocity is dx dt. So effectively what we're doing, this is our function x in terms of t, and we're looking to see what a velocity graph might look like. So we can see at the turning point down the bottom here, dx dt will be 0. On the left hand side of that turning point, so where I've highlighted green, dx dt will be less than 0 and getting more less than 0. And on the right hand side of that point that I've just highlighted in red is where dx dt will be greater than 0 and getting increasingly greater than 0, if you think about what the tangents are doing at that point. So if we want to draw a picture of what that function might look like, we'll mark in some critical points. Now I'm actually going to draw it over the top of this previous function because it's easier. This point here at the turning point is obviously going to be our point of intersection. And because this is a quadratic function, the gradient function or the derivative will be a straight line going through that point there. So it's increasingly getting negative on the left hand side and increasingly getting positive. So that would be a graph of dx dt. Now if we wanted to graph the second derivative function, which I'll do in perhaps blue, we'll think about what sort of slope that is. So we're going to, now we want to graph acceleration equal to dv dt. And to do that, we think, well, that's the slope of the derivative function. So we're looking at the second derivative function now. And if you think about it, that straight line, the red straight line, is a positive gradient. So there'll be some positive function. We don't actually know the value, so we'll just arbitrarily draw it. That function there will be our a equal to dv dt, or the second derivative of displacement. So you can see how we can use the graph to actually sketch key parts of our functions. A slightly more complicated example is this one. So once again, we want to graph the velocity function here. So we want to graph velocity equal to dx dt on this same function. So once again, we're interested in the turning points, because those turning points are going to be where our velocity function is going to cut the axes. We then look on either side of our turning points. So that was our turning point there, and that was our turning point there. So if we look at where I've highlighted red on that graph, if we think about the slopes of the tangents there, they're getting closer and closer to zero at the turning point, obviously, and the further we go away from the turning point, they're actually getting more and more positive. So a tangent at any point to that curve there is getting steeper and steeper and steeper. So we can think about the fact that at this point here, there'll be a turning point on our velocity graph, because that's a point of inflection on the graph. So we do something like that as our velocity graph. So velocity is equal to dx dt, and in this case we can identify the key points being the turning points and also this point of inflection there. Now if we want to draw our acceleration graph on this, so acceleration equal to dv dt, or the second derivative of displacement, this point here will be a key point, because that was the point of inflection, and that's where the gradient will be 0, as that represents the turning point on the derivative graph. And we can think, well, okay, so what sort of a function have I got? To the left-hand side of that, the gradient is negative, so it'll be below the axis, and to the right-hand side, the gradient is positive, so it'll be above the axis. So that blue line might represent the gradient function.